Now, there's different types of protein-mediated transport. Uniport simply means that a protein is transporting a single molecule or ion in one direction. And a good example is glucose uptake into skeletal muscle under resting conditions. This is an example of facilitated transport, but you're moving the molecule in one direction. Another example of uniport is the active transport of calcium out of the cell. Again, it's a protein-mediated transport, but ATPase is supplying the energy. Symport, the same term, is co-transport. This is where a protein is transporting two solids in the same direction. A good example is the sodium-glucose transport or sodium amino acid transport that occurs in the kidney or the small intestine. Now, the opposite situation is referred to as antiport or countertransport. This is also protein-mediated transport, but you're transporting the two substances in the opposite direction. An example here is the countertransport of chloride and bicarbonate across the membrane of a red blood cell then. And again, you went through this in the respiratory section. Now, certain characteristics are common when you have a protein-mediated transport. First of all, in terms of the rate of transport, the transport will be faster if you have those protein carriers in the membrane. This is because the substance does not easily diffuse across the membrane. So the presence of the transporters in the membrane accelerates the transport across the membrane. Now, saturation kinetics is really important to understand. Now, initially, if you supply the substance on one side of the membrane in this protein-mediated transport, as you raise the concentration of the substance on that one side of the membrane, the transport rate increases. The higher the concentration of the substance, the faster it's transported across the membrane until you saturate the carriers. Once you saturate the carriers, you're transporting the substance as fast as you can. And that rate is referred to as Tm, or the transport maximum. By definition, Tm is the rate of transport after you've saturated the carriers. And you should realize it is directly proportional to the number of functioning transporters. If you increase the number of transporters, you increase Tm. If you decrease the number of transporters, you decrease Tm. And this would be a typical question for you on step 1. You are studying glucose transport into a resting skeletal muscle cell. And this is an example of facilitated transport. Suppose you add additional insulin to the medium, what would happen to the Tm of glucose? And this should be your reasoning. If you add additional insulin to the medium, you put more transporters in the membrane, and that would increase Tm. But I want to emphasize, you only reach Tm if you saturate the carriers. Under normal physiological conditions, you do not saturate the carriers. So under resting conditions, you're normally transporting glucose into the resting skeletal muscle cell at a rate below Tm. Now, chemical specificity. For a substance to be transported, it has to have a certain chemical structure. If it doesn't have that structure, it will not be transported by the protein. Now, you should realize only the natural isomer is going to be transported by the protein. D-glucose is the natural isomer of glucose. L-glucose is the non-natural isomer. Now, step 1 can make up any theoretical situation they want to. And you have to draw conclusions from this theoretical situation. For example, suppose they tell you you're studying the membrane transport of glucose then in an in vitro system. and they tell you that the transport of D-glucose across this membrane has the same dynamics as the transport of L-glucose across the membrane. So the dynamics of D and L-glucose are the same across this membrane, and they can ask you what is the most likely method of transport. Now this should be your reasoning. If it was a protein-mediated transport, then because only the natural isomers transport, the dynamics of D-glucose transport would be greater than L-glucose. Because they have the same dynamics, a protein carrier cannot be involved. Therefore, the answer has to be simple diffusion. Now finally, there can be competition for the carrier in the membrane. If you supply another substance of similar chemical structure, it can compete for the carriers. Now you should realize that in vivo, glucose and galactose have almost the same structure, and because they have almost the same structure, they compete for the same carrier. So in vivo, glucose and galactose compete for the same carrier. Now again, they can give you a theoretical situation that you have to evaluate and draw specific conclusions. Suppose they tell you this. You are again studying glucose transport across a membrane in vitro. You're studying the dynamics of the glucose transport across that membrane. Then you add galactose to the medium. But adding galactose to the medium does not change the dynamics of glucose transport. And again, the question is, what is the most likely method of glucose transport across the membrane? Now again, this should be your reasoning. If it was a protein-mediated transport and you added galactose, it would compete for the same carrier. Thus, the initial transport of glucose, the rate should decrease. Because when you added galactose, there's no change in the rate of transport of glucose. Again, the best answer is simple diffusion. And these questions are just testing your overall basic understanding of membrane transport. Now, if we go and take a look at primary and secondary active transport, these are the two types of active transport. Now, in primary active transport, by definition, ATP is consumed directly by the transporting protein. That means the transporting protein has ATPase activity. The transporting protein has enzymatic activity. It can directly break down ATP and use that energy for transport. And a good example is the sodium-potassium pump, which everyone is aware of. And another example is calcium-dependent ATPase. That's a uniport transport of calcium against a concentration and electrical gradient, and you use ATPase, and this would occur in the sarcoplasmic reticulum. Now, in secondary active transport, then, the transporting protein never has ATPase activity. That's the big point here. In secondary active transport, the transporting protein does not have ATPase activity. It indirectly uses ATP as a source of energy. A good example is the co-transport of sodium with glucose in the proximal tubule of the kidney. Now, not in just this example, but in all secondary active transport, then, it utilizes the energy of the sodium-potassium pump. Now, this situation is illustrated on the next page here. Now, this could be a cell lining the proximal tube of the kidney or lining the small intestine. Now, just to orient everyone to the figure here, this represents the interstitial fluid side, so this is referred to as the basal membrane. This is the lumen of the proximal tubule here, So this would be then the luminal membrane. Now, as I just said, all secondary active transport is powered by the sodium-potassium pump. And it turns out in this situation, the pump is located on the basal membrane. Now, the job of this pump is to actively extrude as much sodium as it can from the cell. The job of this pump is to maintain a very low intracellular sodium then. So within the cytoplasm of this cell, just imagine here, I can't put it in here, but you have a very low concentration of sodium. Outside the cell, in the interstitial fluid, you have a very high concentration of sodium. Now, the high concentration of sodium in the interstitial fluid is duplicated in the luminal fluid. Now, secondary active transport takes advantage of the sodium gradient across the membrane. So across this membrane, we have high concentration outside, low concentration inside. And therefore, the gradient then is driving the sodium into the cell, then down its chemical and electrical gradient. Now, there's no reason to simply move sodium in attached to a protein. Instead, another substance moves with the sodium. Now, if it's moving in the same direction as the sodium, it is co-transport. If it moves in the opposite direction, it would be counter-transport. In this case, the glucose is moved in along with the sodium. It's a co-transport. Now, because of the sodium moving in down this electrical chemical gradient, you're pumping the glucose into the cell, and the concentration in the cell increases. So eventually, you're moving glucose from a lower concentration compartment to a higher concentration compartment. It has to be active transport. It is not primary active transport. It is secondary to the pumping of sodium across the basal membrane then. Now, the big point is, this gradient is established by the sodium-potassium pump. And the rate of pumping of glucose depends upon that sodium gradient. If you increase the sodium gradient, the pumping of glucose increases. If you decrease the sodium gradient, the pumping of glucose slows down. Now, this should make sense to you. In fact, you should be able to answer these questions. What would be the consequence for the pumping rate of glucose across the luminal membrane if we slow down the sodium-potassium pump? Now, this should be your reasoning. If you slow down the sodium-potassium pump, the intracellular sodium concentration increases. Because the intracellular sodium concentration increases, you decrease this gradient across the membrane, and the uptake of glucose slows down. Now, suppose instead we change the luminal sodium concentration. If you increase the luminal sodium concentration, you increase the gradient, and you increase the rate of glucose uptake. On the other hand, if you decrease the luminal sodium concentration, you decrease the gradient, and you decrease the uptake of glucose. So the power for this process comes from the sodium-potassium pump, creating the sodium gradient, and the gradient dictates the rate of glucose uptake. Now, the final point to mention here is they may talk about glucose uptake here being directly linked to the uptake of sodium. If they say glucose uptake is directly linked to the uptake of sodium, then you could probably conclude, doesn't conclusively demonstrate, but you can probably conclude it is secondary active transport. Now, we have another example of secondary active transport in the next figure. But the basics are the same. This is, again, the lumen of the proximal tubule, and this is the interstitial fluid right here. So this is the basal membrane, this is the luminal membrane. Now this is just showing the active transport of hydrogen from inside the cell into the lumen here. That's our main focus on this figure right here. This is just another example of secondary active transport in the membrane. Now I don't think I have to go through all the details again. It's basically the same. We have the gradient established by the sodium-potassium pump and the inward movement of sodium down its chemical electrical gradient is pumping the hydrogen from the cell into the luminal fluid. And again here, the rate of pumping of hydrogen is based upon the sodium gradient across that membrane.